Welcome. In this lecture, we will discuss what a fluid is, pressure, Pascal's principle, buoyancy, and sinking and rising. The four states of matter we've mentioned before are solid, liquid, gas, and plasma, and as we also said before, going from left to right requires the adding of energy. In the previous chapter, we talked about solids. In this chapter, we will talk about liquids. Liquids have a non-constant shape, but they maintain a constant volume. And as a reminder, all three of these phases are considered to be fluids. Today, we will mostly be discussing liquids, but a lot of what we will talk about will be applicable to fluids in general. So what is a fluid? A fluid is a collection of molecules randomly arranged and held together by weak cohesive forces and by forces exerted by the walls of a container if the fluid is contained. Another way of defining a fluid is a substance that deforms continuously when acted on by a shearing stress of any size. Liquids and gases and plasmas are fluids, as I mentioned in the previous slide. The study of how these fluids work is called fluid mechanics, but fluid mechanics has two categories: fluid statics, which is the study of incompressible fluids at rest or in stable equilibrium, and fluid dynamics, which is the study of fluids in motion. And as a note, fluid dynamics has subcategories, one of them being aerodynamics, which is the study of air and other gases in motion, and hydrodynamics, which is the study of liquids in motion. This fluid dynamics will be discussed more in the next chapter. Consider a bar clamped on one end and free on the other, with length L and a cross-sectional area A. Suppose a force F is applied on the free end of the bar. What will happen? The bar, under the tensile stress instigated by the force, will of course stretch by some amount delta L. We would say this solid object sustained a tensile stress. Consider a rectangular block of some height h and top surface area A, and imagine it is sitting on a table. Imagine you place your hand on top of the block and apply a shearing force. Friction would then apply a shearing force on the bottom of the block, because the block of course is on a table, and this would be in response to the force that you apply on top. What will happen to the block? It will undergo some small deformation, which is exaggerated here. We would say the block sustained a shearing stress. Solids can sustain tensile stresses and shearing stresses. However, fluids cannot. Imagine pulling on a bar of water, or imagine pushing sideways on the surface of a block of water. The responses of water to that stress would not be the same as the responses of solid objects to that stress. We say, therefore, that static fluids do not sustain tensile stresses or shearing stresses, and they also cannot exert such stresses on objects within the fluid. The only stress that can be exerted on an object submerged in a static fluid is one that tends to compress the object from all sides. In other words, the force exerted by a static fluid on an object is always perpendicular to the surfaces of the object, and that is important for the discussion that follows. The forces exerted by a fluid on the surfaces of a submerged object are always perpendicular to the plane of the surfaces of that object. Imagine that this device is submerged in a fluid of some kind, whether that be air or water. The device consists of an evacuated cylinder, meaning that inside the cylinder is a vacuum, and of course there's the spring that's connected to a piston. So as the device is submerged in a fluid, the fluid will apply some sort of force at the piston, and the piston has some area A. Since the piston is being pushed on, it will move inward, which of course will compress the spring until the inward force exerted by the fluid is balanced by the outward force exerted by the spring. The fluid pressure can be measured directly from this information, given that the spring has been calibrated prior to this experiment. But what is pressure? We haven't even defined it yet. Pressure: the ratio of the magnitude of the force to the area over which that force is applied. So P equals F over A. And the units of pressure are the Pascal. It's important to note that pressure is a scalar quantity, so we use the magnitude of the force. Force, of course, is a vector quantity, so it does have a direction, but we use the magnitude of the force that is applied perpendicular to the surface in question. And then we can define the pressure from that, given the area, of course, that we're looking at. For a tactile demonstration of the definition of pressure and how it's really different than force, mathematically we already saw it's different, but let's approach this from a different vantage point. So hold a tack between your thumb and your forefinger. Now doing so, gently press your thumb and forefinger together. Your thumb will begin to feel pain immediately, while your forefinger will not. The tack is exerting the same force on both the thumb and the forefinger, but the pressure on your thumb is much larger because of the small point, the small area over which that force is applied. So the same force is applied, different pressure, and you notice that in your thumb. Pressure and depth. Let's see how pressure of a static fluid is related to the depth at which the measurement is taken. Consider a container of water. Then imagine we're looking at a parcel of that water, here illustrated as a block of water. The surface area of the top and bottom are denoted as A. And consider the surface of the parcel to be the surface of the full container of the water, or I should say, to be level with the surface of that full container of the water. The height of the parcel is h, and before we draw any forces acting on this parcel of water, let's introduce a reference frame. Ignoring the atmospheric pressure on the water, we are left with only our two forces. You can probably guess at least one of them. First is that gravitational force, and now that we have been introduced to pressure, we know that there will be an upward force applied by the pressure of the water on the parcel. And there are of course other forces on the sides of this parcel pushing inward, but they will cancel out and will not contribute to the motion or the possible motion of this parcel of water. So let's apply Newton's second law. The acceleration of our parcel of water is 0, since by definition we are looking at a static fluid. Now let's write the net force. So we have obviously the gravitational force, which is downward, and we have the pressure, the force produced by the pressure, which is upward, hence it's positive. Let's pull out the unit vector since it's common in both. We can get rid now of the unit vector. Remember, the mass can be written in terms of the density of a substance, as we saw in the previous chapter. So this mass can be written as the density multiplied by the volume. So let's substitute that in. Volume can be written in terms of the area of our parcel and the height of the parcel. So let's substitute that in now. The area A is common in both terms, so we divide both sides by A. Then we solve for a pressure, and we can remove the subscript. Why? Because this is the pressure at any point at some depth h relative to the surface of the fluid, assuming the fluid density remains constant. So the pressure determined in this equation is the pressure at any point in the fluid as measured relative to the top or the surface of that fluid. This is our pressure. This rho is our mass density, this g is still our gravitational field, and this h is our depth relative to the surface of the fluid. Consider two separate depths, the orange dotted line and the purple dotted line. Anything at the depths of the dotted lines experiences the same pressure, but in this illustration, the purple fish experiences greater pressure than the orange fish because the purple fish is at a greater depth than the orange fish relative to the surface of the water. Pressure does not depend on the amount of fluid present. The pressure equation, which we've already seen now, depends just on the depth, not how much water, just how deep you are in the water, for example. So if we look at both of these lakes, there's a large but shallow lake, and there's a small but deep lake. In the small but deep lake, we would say that this lake produces a higher pressure at the bottom because there's a greater depth. Whereas this shallow lake produces a lower pressure because the depth is not as great as the deep lake. Even though the shallow lake has more water, pressure doesn't depend on how much fluid you have, just how deep you can go. Problem number 1. Water pressure provided by a water tower is greater if the tower A is taller, B can hold more water, or C, none of the above. Well, we want greater depth, so we want the water tower to be taller. Because remember, only the depth, not the amount of water, contributes to the pressure. Pascal's principle. Pascal's principle says a change in pressure at any point in a confined, incompressible fluid at rest is transmitted undiminished to all points in the fluid. If I change pressure at one location in a fluid, then at a different location, the pressure changes by an equal amount there. Let's derive this. So let's consider a hydraulic press. And then we're going to actually derive Pascal's principle from things we already know, namely conservation of energy and mass conservation. So we're assuming that this hydraulic press, as we do our derivation, is an ideal machine, meaning that the work that goes into this, or the energy you put in, equals the energy that you put out, and we assume that the fluid, which is that orangish colored stuff, is incompressible, and so it doesn't change its volume. So we're going in with those two assumptions. So we have our piston on the left with area 1, and we have our piston on the right with some area 2. If I apply some force F1, then there will be some force F2 on piston 2. And so both of these pistons will end up moving different amounts, but they will both move. And let's say that piston 1 moved a distance d1 and piston 2 moved a distance d2. So as I mentioned before, we're using two principles here, two conservation laws, in order to arrive at what we've already defined to be Pascal's principle. The first conservation we'll use is conservation of energy, where we know that the work put into the system is the work that you get out. So the work put into piston 1 is the work done on piston 2. And as a reminder, we also are saying that the volume of the fluid within this hydraulic press is conserved. So the volume 1 initially equals the volume 2. Or I should say the volume of the changed amount on the left equals the volume of the changed amount on the right. But let's look at work first. So we know that work is simply force times distance. So we have F1 d1 equals F2 d2. Now let's just rearrange this, and you'll see why a little bit later. Rearrange, and we'll hold on to this equation. So we're going to put it off to the side and bring back our other conservation, which this is really conservation of mass, but we know that this is an incompressible fluid, so we can write this as conservation of volume as well. Now volume is just going to be the area of the piston multiplied by how far it moved. So it's just area times distance. So we have A1 d1 equals A2 d2. And let's rearrange this again. And we have this second equation. So now, bringing back the first equation, we have our two equations. The first one derived from energy conservation, the second one derived from mass conservation with the assumption that our fluid is incompressible. Now we see that the left-hand side of both of these equations is the ratio of d1 over d2. So we can rewrite this as such, which means that F2 over F1 equals A2 over A1. And we'll focus on this here. We can rearrange this such that we now have force over area on the left and on the right. Well, force over area by definition is pressure. So we see that this is actually Pascal's principle, proven when we have an ideal machine. The pressure in one location is going to equal the pressure in another location. Buoyancy. Have you ever tried to push a beach ball down under water? It's difficult because of the large upward force exerted by the water on the ball. Have you ever taken a boat into the water? To move a boat on land, you have to pick it up and carry it. It's heavy. You put it on a trailer and you tow it. But in water, the boat seems very light. You can just push and it'll move. It floats atop the water. But what causes that? Now consider a cube immersed in a fluid. The area of the top and bottom are A. The vertical dimension, as well as the rest of the other dimensions, is D. By definition, it's a cube, so all the dimensions are the same. According to what we've seen in previous slides, the pressure at the bottom of the cube is less than the pressure at the top due to the difference in depth relative to the surface of the fluid, which is water in this case. So the pressure at the bottom produces an upward force, and the pressure at the top produces a downward force. But the depths are different, so these forces are going to be different. So what is the resultant force produced by the difference? Well, this is actually going to be the buoyant force. So the buoyant force equals the sum of these two forces. But using the same reference frame we used before, we know that one of these will be negative and one of them will be positive. So let's put in our definitions there, where the force is just the pressure multiplied by the area. Let's now factor out our unit vector y, and let's remember that pressure is, by definition, equal to the density multiplied by the gravitational field multiplied by the depth. And we can do that for both of these. And we can plug that in, and we can pull out our common terms such that we have the density of the fluid multiplied by the gravitational field, multiplied by the area, the surface area of the block, multiplied by the difference in depth from the top of the block to the bottom. And this is really just our distance from the top of the block to the bottom. So we can replace this whole thing with d. And of course we know that A times D is the volume of the object, so we can replace that just with V, and we know that this is the buoyant force. This difference in force that is created by the differences in the pressure is the buoyant force. So the magnitude of the buoyant force is shown below, where this rho, importantly, is the density of the fluid, not the density of the object, it's the density of the fluid. This is the gravitational field, and this is the volume of the displaced fluid. Now, the volume of the displaced fluid is equal to the volume of the object if the object is completely submerged. If the object is floating, only part of the object is beneath the fluid or under the fluid, so the fluid that has to move out of the way to make room for the object is not equal to the volume of the entire object. What happens if I rearrange this equation now? Well, rho times V, that's just mass. So this would be the mass of the displaced fluid. So we can say that the buoyant force equals the weight of the amount of fluid that had to move out of the way. So it's the weight of the displaced fluid. This is actually Archimedes' principle. An immersed object is buoyed up by a force equal to the weight of the displaced fluid. Let's consider an example. If I take this rock and I submerge it in the water, you expect that the water level will rise by some amount. Now the volume that we see here is actually the volume of the stone. So this cross-hatched volume of water is the volume of the stone, because water had to move out of the way to make space for the stone. Well, how much water? Well, an amount of water equal to the volume of the stone had to move so that the stone could be there. And it just so happens, based on what we showed in the previous slide, that the weight of this water is the buoyant force on the stone. So the weight of the water, the fluid that had to move out of the way, that was displaced, is exactly the buoyant force applied to the stone. If we take a slightly different example, but same principle here, we have a beaker that is fully filled, and then we put the stone into it. Well, the amount of water that had to move out of the way is the volume of the stone. And as we said before, the weight of this water is the buoyant force on the stone. Problem number 2. Which object experiences the greater force of buoyancy, the wood block or the stone block? Well, the stone block would. Why? Because it displaces more water. Assuming that these cubes of one being wood, one being stone are of the same size, well, the stone is at the bottom, it's completely submerged, so more water had to move out of the way to make room for this stone. So, since the stone block displaces more water, then the buoyant force on the stone rock is greater. But you say, oh, but it's not floating. So how can the buoyant force on the stone be larger than the buoyant force on the wood while the wood is floating? Whether something sinks or rises doesn't just depend on the buoyant force, it depends also on how much the object weighs. And that leads us to the next topic, sinking and rising. Whether an object sinks, rises, or does neither depends on both the buoyant force and the gravitational force on the object. So we have the gravitational force down and the buoyant force up. And let's write our reference frame, and let's do Newton's second law. The net force equals the mass multiplied by the acceleration. Well, what are the two forces? Well, we have the buoyant force and the gravitational force. And we can plug in their magnitudes using the unit vectors to guide us. And we see that the buoyant force is positive, it's pointed upward. The gravitational force is downward, so it's negative. And we can remove the unit vector because it's common in all the terms. And we can solve for the acceleration. Why? Because acceleration tells us how the state of motion of an object will change. So it will tell us whether something's sinking, rising, or not doing either, assuming that it begins at rest. So from this equation, we can tell that if the buoyant force is greater than the gravitational force, or the weight, then the acceleration is positive, which means the object will rise. If the buoyant force is less than the weight, then the acceleration is negative and the object will sink. If the buoyant force equals the weight, then the acceleration is 0 and the object will neither sink nor rise. Let's talk about this last case for a little bit. And let's talk about it in the context of floating. And it's a specific case when the buoyant force equals the weight of an object. And this leads us to the principle of flotation, which I don't know why it's set aside as its special own deal, but it is. So the floating object displaces a weight of fluid equal to its own weight. So if we consider a ship, an empty ship, it's floating here because the weight downward equals the buoyant force upward. What if you put more weight on the ship? So let's say that in our first example, the ship is empty, but then you load it up with a bunch of supplies. Well, now the ship is going to weigh more. Well, how do you increase the buoyant force? Well, the ship will sink further into the water, forcing more water to be displaced. If more water is displaced, then the buoyant force on the ship increases because we know that the buoyant force is equal to the weight of the displaced fluid. If you displace more fluid, you increase the buoyant force on the object. Okay, let's return to what we had. So whether an object sinks, rises, or does neither can also be determined by relative densities. Now remember, the buoyant force is equal to the density of the fluid multiplied by the gravitational acceleration multiplied by the volume, and the weight of the object is just, well, the mass of the object multiplied by the gravitational field. Let's substitute those both in, and we remember that the mass of an object can be written in terms of its density. So we can say the density of the object multiplied by the volume of the object. Do the same thing in the denominator. We could substitute that in, and we can pull out our common terms, and we see that there's also volume now is common between the numerator and the denominator. We can cancel that out, and it simply leaves us with, in the numerator, a difference in density. So this tells us if the density of the fluid is greater than the density of the object, then the acceleration will be positive, which is upward based on our convention, and the object will rise. If the density of the fluid is less than the density of the object, then the acceleration will be negative, which is downward in this case, and the object will sink. If the densities are equal, then the acceleration is 0, and the object will neither sink nor rise. So in summary, we discussed fluids, pressure, Pascal's principle, buoyancy, and sinking and rising. I'll see you next time.